In this video, I'm going to give you a brief overview of three of the most prominent interpretations of quantum mechanics. The first one that we'll discuss is called the Copenhagen Interpretation, and we'll go through it pretty quickly because it's basically the interpretation that I've been teaching you so far. The Copenhagen Interpretation is essentially the standard interpretation of quantum mechanics. It's what you're most likely to hear about or read about in a popular science medium of any kind. It's what you'd learn when studying quantum mechanics in college or graduate school, and it's the framework within which most calculations are done for practical purposes, as well as the framework within much of the language of quantum mechanics is kind of defined. This doesn't mean that the Copenhagen interpretation is right or even the best interpretation, but it is one of the oldest interpretations that we have, and it can be traced back to the 1920s to two physicists named Werner Heisenberg and Niels Bohr, and that's actually where it gets its name. The two of them were doing work in the 1920s at the Bohr Institute in Copenhagen, and that's ultimately where it got its name. The Copenhagen interpretation isn't really one interpretation. It's really more of a whole class of interpretations. Different physicists might mean slightly different things when they say the Copenhagen interpretation. In fact, even Bohr and Heisenberg had some differences of opinion when it comes to how certain elements of it should be interpreted. And of course, in the subsequent century, there's been a great deal of developments and additions and modifications. So what I'm going to do here is I'm going to talk about some of the basic features that are common to what almost everybody would mean if they are talking about a Copenhagen interpretation. The first of these principles is that the wave function describing the state of a system completely describes everything about the system. There are no additional properties, there are no hidden values, or anything else. The wave function describes all that there is. Here I should clarify that the wave functions we've been using up to this point are not actually the total wave function of the system. We've only been looking at the little piece of the system's wave function that describes its spin. In reality, the wave function describing the system encapsulates all the information about it, including position, amplitudes, and anything about its charge, its mass, and so on. All of that information is encoded within the wave function of the system. And we have so far only been dealing with a small piece of that. The second is that physical systems don't generally have definite properties until they're measured. Measurement of a system will collapse the wave function of the system into one of the measurement's eigenstates. And wave function collapse is a probabilistic process where all the different possible eigenstates probabilities are determined by their probability amplitudes. The Copenhagen interpretation is usually considered by most people to be an epistemic interpretation of quantum mechanics as opposed to an ontological interpretation. Epistemic means of or relating to information or knowledge, whereas ontological means of or related to the state of physical being. So when I say that the Copenhagen interpretation is epistemic, what I mean is that the wave function is not considered to be a physically real object. We're not performing measurements of wave functions. We're performing measurements of electrons, and the wave function is simply something we use to describe the state of the electron. This is a very sort of high-level description of the interpretation. It doesn't go into all the details and subtleties. It doesn't address, what the implications are for various phenomena like entanglement and superposition and so on. But it is the general idea that is common to almost all interpretations that people would consider a Copenhagen interpretation. There are a lot of other interpretations that also incorporate wave function collapse in some form, such as quantum Bayesianism, objective collapse theories, consciousness causes collapse interpretations, and so on. But the other two that I'm going to talk about in this video actually don't include wave function collapse. The next one on the list is called Broglie-Bohm theory, also often referred to as Bohmian mechanics or pilot wave theory. There are technically possibly some historical differences between these, but for our purposes, they describe the same thing. Broglie-Bohm theory is a hidden variable theory, but it's consistent with our observed violations of Bell's inequalities because it's inherently non-local. In fact, it's non-local to a much greater extent even than, for example, the Copenhagen interpretation is. So here's the gist of how it works. First of all, in this interpretation, systems possess definite properties. There is none of this quantum indeterminacy or fuzziness exhibited by the Copenhagen interpretation. There isn't really quantum superposition in the way that we've learned it. There's the illusion of indeterminacy caused by our lack of a complete understanding of all the information about a system, but in reality, a particle has a definite spin, whether we know it or not, in all circumstances. In order to discuss the details of this interpretation, it's easier to work with the concept of position rather than spin. We haven't really talked about the quantum mechanics of the position of a particle, not yet anyways, but it really exhibits essentially the same behaviors as spin does. In the Copenhagen interpretation, for example, particles can exist in a superposition of position states as well as spin states. So a particle's position is not really well defined until the particle's position is measured by some kind of observation or experiment. I'm going to describe this interpretation in terms of position, again, just because it's simpler, but you should be aware that it does generalize to other properties as well. Strangely enough, the so-called hidden variables of this interpretation are actually the positions of the particles themselves. That might seem like a wacky concept because I can look at things. You can see where things are. How is that hidden? Well, in a quantum mechanical sense, the precise positions of particles isn't possible to determine exactly. No matter how good your tools, any measurement of a system necessarily disturbs that system. For example, even when you look at things, you're seeing light that came from that object, but the emission or reflection of that light actually has an effect on the position of that object, on whatever the light came from or bounced off of. So where you see the object is not necessarily where the object is. In other words, this interpretation posits that systems do possess definite properties, including position, and yet it's impossible to actually determine the precise position of a particle. Therefore, the precise position of a particle is a property that it has that cannot actually be determined, and therefore it's a hidden variable. The term hidden variable is maybe not the best choice of term, but it is, unfortunately, what we're stuck with. Another important feature of the Broglie-Bohm interpretation is there is no such thing really as the wave function of an electron or the wave function of an atom, but rather there is only the universal wave function. The universal wave function is really the same wave function we've been talking about. It's just that it is the wave function of everything. It's the wave function of the system that includes the whole universe. It is nonetheless calculated the same way as wave functions in any other interpretation, which is to say that the wave function can be calculated by the Schrödinger equation, which we haven't talked about yet, but we will in the near future. This is actually where the non-locality of the interpretation comes into play. The value of the universal wave function at any particular position depends on everything in the universe. It doesn't matter how far away it is, it can be affected by anything else. It doesn't mean the effect has to be strong. Typically, the farther away things are, the smaller of an effect they'll have on the value at any given place, but that's not necessarily always the case. There's an additional piece of structure in this interpretation called a guiding equation. The guiding equation essentially tells particles how to move as a function of the universal wave function. A very simplistic way of thinking about this, and in fact, a not entirely correct way of thinking about this, is imagine a particle at some position, and now let's imagine we know what the wave function is, and depending on the value of the wave function at the position of the particle will end up essentially being pushed around or guided by the wave function, again, according to the guiding equation. I want to emphasize that this was meant as a very loose analogy. The particle is not literally pushed around by the sort of wave pattern as I just demonstrated. In reality, the details of how the value of the wave function affects the velocity of the particle is quite complicated, especially when you remember that the wave function is actually a complex valued function. And, in fact, even a static wave function can result in moving a particle around. But the point is that the wave function literally does guide the motion of the particles, and it does so according to the rules of the guiding equation. An important feature of the Broglie-Bohm interpretation is that it is completely deterministic. Things appear probabilistic because we can never actually know the exact position of a particle, which means we can never predict exactly what the particle will do because we don't know what the precise value of the wave function is at the particle's current position. This reproduces the randomness that we see in our experiments, but for very different reasons. Here, the apparent randomness in our observations is accounted for by the fact that we don't actually have and can never even have complete knowledge of the system. There is information about the nature of the system that is inaccessible to us. This is different from the Copenhagen interpretation, where the wave function is all the information there is. We're not missing anything, it's just that all the information there is insufficient to predict what will happen. When it comes to predictions that we can make about the systems that we observe, there's no difference between this interpretation and the Copenhagen interpretation. They really do result in the same thing. It's just that they choose to describe the nature of reality differently. The third interpretation I want to introduce to you is the ManyWorlds interpretation of quantum mechanics. This interpretation can be thought of as simply taking the wave function literally. Essentially, in order to understand or describe quantum mechanical systems, we've had to invent this construction that we call a wave function. And on top of that, in our other interpretations, we've had to come up with elaborate schemes of how to turn that wave function into things that are measurable, whether it's wave function collapse of the Copenhagen interpretation or the guiding equation of the Broglie-Bohm interpretation. ManyWorlds says, no, there's no such thing as either of those. There's just the wave function, and the wave function evolves over time according to the Schrödinger equation. That's just what the wave function does. And if that's all there is to it, then the concept of superposition takes on a very different meaning. Instead of there being multiple possible outcomes of a particular measurement, there are different outcomes of that measurement. Consider, for example, a particle in a superposition of spin up and spin down, as well as the wave function of you, the observer. ManyWorlds is similar to the Broglie-Bohm interpretation in that it also supposes that there really is only one wave function, the universal wave function describing everything in the universe. So for this little demonstration, let's consider that you and this electron are the only things in the universe. In that case, the universal wave function is described by the direct product of the electron's wave function with your wave function, just like we did with these two particle states before. In the Copenhagen interpretation, what I've been teaching you, if you perform a measurement on the state of the electron, you will collapse the wave function into one of these two possible outcomes, into one of the eigenstates of your measurement. In this case, the wave function would collapse either into the combination of a spin-up electron with you with the memory that the electron was spin up, or it would collapse into the electron having spin down and you with the memory of the electron being spin down. Before you made the measurement, you didn't know what the spin of the electron was going to be. So in fact, we can go back and we can say that prior to the measurement, you were wondering what the spin would be. In the ManyWorlds interpretation, this measurement process is very different. There is no wave function collapse. The wave function is really just all that there is. And so we start out with this separable state where regardless of what the state of the electron is, you have no idea. So your state is independent of the state of the electron. But once you measure the state of the electron, you become entangled with it. And so the wave function evolves. Instead of being separable like this, it turns into an entangled state, corresponding to the combination of the particle being spin up and you having found it spin up, and the particle being spin down and you having found it spin down. So what is the outcome of the experiment? Both. How is that possible? What are you going to find? When you run the experiment, do you find that the particle is spin up or that it's spin down? Again, both. Future you will find the particle spin up and create the memory of finding the particle spin up. But future you will also find the particle spin down and create the memory of finding the particle in the spin down state. But these two versions of you are unaware of the other. There's no mixing between those two terms, so the version of you with the memory of finding the particle and spin up has no knowledge about the version of you that found the particle to be spin down. Hence, the ManyWorlds interpretation. The ManyWorlds interpretation effectively says every possible outcome of any interaction or measurement does occur. There is no random selection process that picks out one of the possible outcomes. There is no hidden information about which of the outcomes will actually occur that we as the experimenters simply don't have access to. It's simply that all of the outcomes happen. You don't have one future. You have every possible future. It's worth mentioning that this is not the multiple universes trope that shows up in science fiction all the time. You don't literally split in two when this happens. For example, you have mass, the electron has mass. The amount of mass before and after the measurement is no different. These two versions of you share the same mass because these are simply represent the components of the universal wave function that describe the combination of particles that we refer to as you. This process is referred to as decoherence. We start out with a universal wave function in which the state of the electron and the state of you are independent of each other. But then when you go and you look at the electron state and your state become entangled with each other. Once that happens, we essentially create branching histories. And so the ManyWorlds interpretation is the idea that as different parts of the universal wave function interact with each other, decoherence occurs and kind of clumps them together into the sort of different combinations of possible ways that those systems can interact with each other. And it posits that each of those histories, if you will, are real. But there is no duplication of particles. It's not like there was one electron and now there are two electrons. This plus and this minus refer to the same electron. The version of you with the memory of finding the spin-up particle and the version of you with the memory of finding the spin-down particle describe the same you. It describes the same set of particles. It's simply that there are now two different histories for those particles that make up you. These two versions of you could never meet. You could never find a portal and cross from one world, if you will, into the other, because this and this refer to the exact same collection of particles. In some sense, you can think of superposition as being sort of manifestly real in this case. A particle can literally be spin up and spin down at the same time while still being one particle. And the particle being spin up and the particle being spin down are totally sort of orthogonal to each other. And that reasoning applies to collections of particles too, such as the collection of particles that we call you. This is the point that I really want to emphasize. ManyWorlds in some ways is not the best name for this. In an alternative name, it's not very common, but I think perhaps a better description is the many histories interpretation. It's not that entire new universes filled with a whole new universe full of mass and charge and all those fun things pops into existence every time particles interact with each other. Instead, the same world simply has branching histories. This interpretation leads to all kinds of fun, hypothetical scenarios. One of my favorites is called quantum immortality. And what it says is that if there exists a non-zero probability for you to survive into the next moment according to the wave function, then there is some history in which you do survive. And if the probability of you surviving into the next moment never goes to zero identically, then there is always some history in which you are still alive. This sort of thought experiment, has actually been turned into short stories, some of which are really interesting and thought-provoking, and also in some ways very disconcerting. At least as of now, we have no way of experimentally distinguishing between any of these interpretations. There are some limitations of some that others don't have. Some have features that are preferable over others and so on, but in the end, they make the same experimental predictions. If anything, de Broglie-Bohm is probably the sort of least rigorous just because it's not been developed to quite the same extent. It's unclear whether it's truly consistent with more rigorous formulations of quantum mechanics like quantum field theory and so on. But to me, the ManyWorlds interpretation is the most interesting. I think it's the most wondrous interpretation of the world. And you might think that physicists would just kind of like dismiss it as being a little bit too crazy, but in fact, ManyWorlds is probably the second most common interpretation of quantum mechanics after the Copenhagen interpretation. Although I should really say, of people who have chosen to kind of pick an interpretation, a great number of physicists actually subscribe to a totally different interpretation of quantum mechanics, which is the Richard Feynman's shut up and calculate interpretation. Because we cannot experimentally distinguish between many of these interpretations, a lot of physicists believe that there's no point in really even talking about it and accept that quantum mechanics is a mathematical model. It doesn't really seek to describe what is physically real and what is physically happening. It simply is a tool that allows us to predict what we will find when we perform a measurement. The descriptions of the interpretations I've given you here are sort of high-level descriptions. I've left out a lot of the important details and subtleties, but what I have covered to a large extent are what I view as some of the sticking points, some of the concepts or aspects of these interpretations that can be difficult to wrap your head around if you've never been exposed to them before, and especially when you're new to quantum mechanics in the first place. And so at this point, I'm leaving it to you to make use of other more rigorous resources that you can find in order to build a more complete understanding of these different interpretations of quantum mechanics.